There we go. And quick test, do you see a slide with a single slide on it?
Yes, we can see a slide.
Okay, awesome. All right, thank you so much for the invitation. It's always really fun to get back to UPenn, even if it's virtual this time. What I'm doing today actually is I resisted the temptation to talk about my latest, deep learning stuff that I'm working on, and instead I'm actually presenting work that seems fairly old. Maybe it's from 2014. It's a talk from 2014. Actually, I made very small changes to the slides. And there's two reasons for this. A, because it nails the venue exactly. So this is work that I did 6-7 years ago, but it's exactly about this topic, like learning with, we called it a corruption back then, marginalized corruption. Now it's called augmentation. And so for a workshop like this, it may actually be interesting to see kind of what was done back in the day. The other thing, there's a personal reason. I would like to dedicate this talk to my friend and colleague, Olivier Chappelle, who sadly is no longer amongst us. And Olivier was my mentor and was one of the early people at NeurIPS. And he was actually someone who wrote one of the first papers on data augmentation and machine learning, which was vicinal risk minimization in 2001, the NeurIPS paper, together with Vapnik and Leon Boteau. And actually, there's a connection to this work because I wasn't actually aware of this work when I did my marginalized corruption work. And we realized at some point that while we were writing this, that Olivier actually had discovered one of the theorems already in his 2001 paper a long time before and was way ahead of his time. All right, so let me just frame the setup. So I'm talking about risk minimization and not, Olivier talks about vicinal risk minimization. I get into this in a minute. Let's just talk about standard empirical risk minimization. So machine learning basically always has the setup, right? You have a loss function and you have a regularizer. And the loss function does the job where it basically says, try to fit the data point as well as possible, right? And if you do this, well, it always works. You get zero training error, provided you have a powerful enough learner. The loss functions that we are looking at in this talk are threefold: exponential loss, the squared loss, and the logistic loss. And so I guess it doesn't need a lot of introduction in this crowd. Essentially, the idea is, here in this case, I'm focusing on linear classifiers. You could also imagine this could be the output of a deep net, then it would be nonlinear. And essentially, you multiply with the label is +1, -1. So if the inner products disagree, then this is very, very large, you suffer a lot loss. And if it's small, then you suffer a small loss. So basically it says, get every single point correct, like get it on the right side of the hyperplane. The second term here is the regularizer. And the regularizer has a simple job. It says, keep it simple, right? So, and typical regularizers are L2 regularization, L1 regularization. Nowadays, people also regularize by using SGD, and this is kind of implicit regularization. And this setup, this canonical setup in machine learning is somewhat a tension, right, between these two terms. So the loss says, get every single label right in the training data set, and the regularizer says, no, keep it simple, right? Like it's okay to sacrifice some training points, keep it simple. And I claim that a lot of the errors, problems of machine learning in practice are due to this tension, right? Like not getting this tension right, like overfitting too much or keeping the model, like over-regularizing it, etc. And the other thing is, it's hard to somewhat get this right. What is the right regularizer? Because these are somewhat intuitive and arbitrary, right? Like, L2 regularization or weight decay, that's called in neural networks. It's, somewhat an arbitrary thing to do. So it would be nicer if we could actually give practitioners who use machine learning a chance to, use the understanding of the data to, reduce the complexity of the model, or to avoid overfitting. And this is essentially where data augmentation comes in. So the problem, of course, always is that we don't have enough data. If you have infinite amount of data, machine learning becomes really, really simple. You don't need a regularizer. You just need a loss. You just fit it. You're good to go. Because you go over your data many times, you start to overfit, and you have to avoid this. So an alternative to regularization is data augmentation, or we called it corruption back then. And so the idea is very simple. For every single data point, this is your data set here, blue and red points. And for every single data point, you draw new corrupted versions of the original data point. So for example, for this point, I'm just drawing some other random, corrupted versions of this data point. And so I'm pretending I'm artificially increasing my data set size. Right? And so the hope is that by doing this, I'm getting into the regime where regularization doesn't matter anymore, right? Where I'm actually just naturally just minimizing the loss function does the right thing, and my learning becomes easier. Also, of course, the hope is that during test time, if I see some of these points, I may generalize better. And so the very, very early work from 2001 that Olivier Chappelle did was basically assumed that it's a Gaussian distribution. And if you have a Gaussian distribution, then everything becomes very nicely. The other thing actually is this is related to max margin, the theory of max margin, because if I say every single data point has to be far away from the hyperplane, well, if I say this data point this teeny little data point becomes a big ball, right? Then what happens is I'm introducing a margin, right? So this is, I guess the connection that Babnik and Olivier already made a long, long time ago, 20 years ago. Okay, so, and here comes the cool part, of course, that the corruption distribution can be chosen by the practitioner. So, just to give you some examples. So here let's say we have an image here. This is nowadays, of course, augmentation is a big deal in computer vision. There's many, many very fancy ways of doing this. But we just thought, well, here's one thing. You can just, for example, drop the data. I don't know if you can see this animation. I hope you can. I'm basically just dropping pixels and just make them black. So we call it blank out noise. And you can still see that it's a car, right? So nothing much changed. So here a picture of a gentleman. It's actually Carl Friedrich Gauss. And I corrupt him with, well, Gaussian noise, right? He had it coming. And as you can see, he's still the same guy, right? Despite that I'm corrupting this image. And so now I'm getting millions of different versions of this image that are all slightly different. Same thing here, I have a text document, this is a bag of word vector, I have the word amazing 5 times, seems like a very positive description of something. If I change this to just 4 times, it wouldn't change much, so it's still a positive text. Okay, and so one thing that's very, very important in this slide is that we are basically corrupting the data, but one assumption we are making here is that each dimension is corrupted independently from the other dimensions. So let me just formalize this. We have a data point X, we draw a new data point X tilde, which is the corrupted version of this. And we can do this as often as we want. And we say the probability is basically that we go by every single dimension. And for each dimension, we just randomly draw a new value for this dimension, right? So in this case, the fact that we changed that amazing does not affect how we change the word keep, the counts for keep. Okay, so we can try this, right? And so this is now an experiment we did, of course a little dated now, but here we have movie reviews. These are from Amazon, collected by John Blitzer, who's also a Penn alumni, actually. And so here are some negative reviews. They just have 1 star. These are positive reviews. They have many stars. And so this is just a binary problem. Is a review positive? That means 4 or 5 stars. Or is it negative, 1, 2 stars? And I think 3 stars were removed. And so what we can do now is we can take these reviews and we can just replicate them and make corrupted versions of each one of them, right? So each review, basically, we just replicate a couple of times and we just randomly remove words, right? So here we just essentially kind of blank out these words. And for each, the way we do this is for every single word, we just go through it and we just toss a coin. And if that coin is head, then we just say this word is removed from this particular position. So this is the data corruption process. And so just in terms of misminimization, what does it look like? Beforehand, we went over all our data points, 1 to n, and we minimized this loss, right? This is, now you can do gradient descent or whatever. And so now we go over every single data point. And for each data point, we make m copies and we minimize the loss of these m copies. And these m copies are basically drawn from this corruption distribution that we specified. In this case, we just take every single word and drop it with probability p. So when we do this, and this actually, by the way, there's a paper that even predates this, Olivier Chappelle's work from Burgess and Shurkov. So in 1997, they proposed this in support vector machines. And so here's the error, and I apologize to all mathematicians or anyone who cares about the x-axis here. This is logarithmic, but I snuck in the 0 here just to have. I should have maybe just been a horizontal line. But so what does this mean? This is a function of what is the test error given how many corrupted copies I had of my training data set. And I think I had I think 2,000 training samples here. And so if I don't do any corruption, this is the best I can do with hyperparameter search, 18% error. And now as I increase the number of corrupted samples, I increase my training data set size. Basically, what you see is, oh yeah, the error goes down very, very nicely, right? So this really works. And this, yes, we know data augmentation works. Yeah. But there's one thing that's very interesting, is that, well, we can drop the error from 18 to 14.5, which is a pretty big deal, right? But if you look at the x-axis, what you see is that this is logarithmic here. To get there, we also made it 256 times slower, right? So if you want to compute the gradient of this function, you use some second order method, right? You actually have to go over 256 times the data set. So in practice, people never do this for linear classifiers. So people would do just this, right? So they just go over the data set a couple times, right? Each data, or each sample is just corrupted a few times. And then that's where you get the biggest bang for the buck, right? Like you just go over, you increase the data set a little bit, but you get a big drop here. And it's not worth going all the way down here. So we thought something else. We thought, well, what if instead of keeping M small, right, we make M really, really, really large. And so here's the idea. Here's the loss function that we have. We minimize 1 over n, and we go over these M copies. And what if you make M go to infinity? Then actually this sum here, if you look closely, right, is of course becomes the, this becomes the expected value, right? So here we go over the loss over all our M copies, we average it. If M goes to infinity, this just becomes the average loss that you would get if you draw, or the expected loss that you would get if you draw corrupted versions from, sorry, someone doesn't have their mic muted. I think, Mark, it's you. Anyway, I just keep going. So there's the expected, so you minimize the expected loss under this corruption distribution. So basically what you're saying is, if I were to corrupt my sample, what would be the expected loss? Now, of course, that's neat, right? But this expected value could be really nasty to compute. Can we compute this? And the answer is actually amazingly, yes, we can. So in some sense, we're creating a new loss function, right? This is this expected value of this loss function. And so I will go through this in a minute. So just one more time, we're basically saying, we're going over our data set, we are corrupting each sample, right? And we do this from each sample, we actually now generate infinitely many samples that are corrupted. In the limit, it just becomes a new loss function. And the new loss function is the following. I go to every single sample. And then what I'm minimizing is not the loss, but it's the expected loss under corruption. And so for certain loss functions, this actually can be computed. So let's go through the 3 loss functions that I mentioned earlier. The first one is the exponential loss. So you can make this guy smaller here. So is the exponential loss. And so the expected value of this exponential loss, if you look closely, right, actually, so the first thing we can do is we can actually, this is an inner product here. So it's a sum, right, in the exponent. A sum in the exponent is just a product of many exponentiated values. So this is just, we take this, because they're independent, we can pull this product out. That's easy. Now we have this function here. And this function here actually has a very, very beautiful property. It's actually a very well-known function. It's the moment generating function of this distribution. And so for all of you who remember stats 101, right, the moment generating function, well, statisticians love the moment generating function. It has many amazing properties. And most importantly, it's actually already pre-computed, right? So for all of these distributions, people have computed these moment generating functions. So you just go to Wikipedia, look up what it is, and you plug it into the equation here. And that's the new loss function. So instead of minimizing loss, you minimize the moment generating function of loss. So for various noise corruptions, I can just compute this. I can just look this up. Another one is the log loss. That's nowadays what everybody uses in neural networks, but it's like logistic regression, etc. So here actually it doesn't work as nicely in closed form, but what we can do is we can use Jensen's inequality, and then we can push the expected value in here. And again, we get the moment generating function. And so essentially what we can do is we can build an upper bound. Last but not least, the quadratic loss. Quadratic loss is very nice. because everything, we don't even need moment generating functions, everything just becomes in terms of expected value of the corruption and the variance of the corruption distribution. So we get a closed form solution, which just depends on the first and second moment of the corruption distribution. And this is actually something that Olivier Chappelle wrote in 2001 about, and he actually also showed, and you know, of course, it just pops out right away out of the equations, that if you have a Gaussian corruption distribution and square loss, you get exactly ridge regression. So ridge regression actually is doing this. All right, so again, if you have different noise distributions, these are the first, second moments. So these are kind of the equations you can just plug in here, and you get different loss functions. All right, so now if you go back to our example with these reviews, here's what we can do. We can now actually plug in this, we had blank out noise here. We can actually now, you know, minimize this expected loss. And this is the error we are getting, right? So the cool thing is we now have the computation complexity of here, right? We only have our n data points, and we're minimizing just a different loss function, right? And the different loss function is exactly equivalent to going over infinitely many copies of your data set, right? So instead of, you know, making it really, really slow by doing all this corruption, we actually don't even do it, right? We just compute it in closed form, this loss function, and we actually get another drop here. So that's what we call marginalized corruption. One more time, so how does marginalized corruption work? It's very simple. So the first thing is you pick a loss function of your choice. Poof, in this case, that's the exponential loss. Then you pick a corruption distribution of your choice, and it always pops out so nicely if it's from the exponential family. So you read the blank out noise, good. And so what we have here is we just look up the moment generating function of this corruption distribution. And now we just substitute this part here with the moment generating function, and that becomes our loss function. And this is a new loss function that we generated basically, you know, for this problem. And the nice thing is essentially the practitioner can say, right, does blank out noise make sense? Right? Look, for some setting that may make a lot of sense. For some setting it doesn't make sense, right? So maybe you should use Poisson distribution or something to corrupt your noise, etc. So here's where you really can see that this talk is dated. I used MATLAB. Nobody uses MATLAB anymore. But in MATLAB, this is just 4 lines of code. Of course, if you use Python, PyTorch, this is exactly, you know, it's just as short. So the cool thing is really this is very, very minimal amount of overhead when you implement your machine learning algorithms. It's trivial. Okay, so a few results. Again, these are from back then, but this is here, review classification is a review positive or not. But the interesting thing is here, what we see here is basically the probability. This is just blank out noise. So we just remove words. 0 is the probability of basically, you have a 0 probability of removing any words. So you're not removing anything. And now if you keep, so these are different loss functions. This is quadratic, this is exponential, and this is logistic. And if you now go down here, if you increase the probability of removing things, then actually what you see is the error goes down very, very nicely. These horizontal line here are Poisson, if you use Poisson corruption, which actually has no parameters in this setting. And so, yeah, everywhere is the same trend that basically, you know, what you see is that there's this one parameter basically saying, what's the probability of corruption? That's a parameter of your corruption distribution. Like what's, for every single word, what's the probability that I remove it? And as I increase this, that tends to tend to get lower error. Of course, if I were to go to 1, then actually I would just remove everything. And if I remove everything, of course, the error would shoot up again. Here's another text classification data set, same trend. This is a trend of number of training samples. You see it initially actually get a benefit from, you know, number of, well, let me not get into this too much. The last thing is the Cypher 10. This is a little comical now because now we are at 3% error on Cypher 10. Back then it was a pretty new data set, and these are actually the state-of-the-art results at the time, because this was not deep features yet. This was bag of word features with interest points. But again, so what we used here what you can see is what's very nice is that here Poisson distribution actually makes a lot of sense. So this is without this is the error without marginalized corrupted features, and then if you use Poisson or blank out features. And Poisson here seems to make a lot of sense. Okay, good. I have probably still a couple of minutes. So when we did this, it was right around the time where deep learning kind of started its rise and its craze. So we were also interested in the connection here. And one particular setup that we were interested in was domain adaptation. And so domain adaptation, just for those who may be not familiar with it, is very simple. During training time, I have a data set, I'm learning a classifier, but then during test time, my data set shifts. So I have a slightly different test set than I have a test data distribution than I have training data distribution. And I'm looking at sentiment analysis here. And so sentiment analysis actually is a really, really big deal. So sentiment analysis basically says something positive or negative. So here's actually where domain adaptation really kicks in. Why is this? Because you have a lot of reviews. You can always train on reviews. Reviews are really great, right? You have millions of reviews on Yelp and Amazon and so on. But what you really want is classify things where you don't have a training data on. So for example, let's say Apple, I think, is releasing a new watch this month. If you are a stock market broker or something, right, then what you want to know is, as quickly as possible, how does the public receive this new gadget, right? Those guys, the early adopters who immediately bought it, how do they like it? What do they think about it? So what you do is you run a sentiment analysis algorithm over the blogosphere, over Twitter. You try to feedback as quickly as possible and say, okay, overall people don't like the watch, so let me short sell Apple stock or something. And actually turns out it's $1 billion industry. Same thing, actually politicians do this to see, what opinion their constituency is about a certain topic. So anyway, so the setup is we train on reviews, and on one set of reviews we test on another, essentially. The interesting thing is that there's a difference in domain. So there are some words that are kind of indicative of sentiment across both domains. For example, here, elegance, amazing, great. You can describe a gadget that way. You can describe a book that way. Some are very target specific. Battery life, for example, you can say something that's great battery life, that's good. If you say a book has great battery life, that doesn't make any sense, so you wouldn't say it. And there's something that basically that's very source specific. So this is very eloquent, best written. You wouldn't say that about a watch because it makes no sense. So you basically have some words that you use it regardless of the domain. Some you only use in target, some you only use in source. Okay, so there's a big domain adaptation data set where basically people, John Blitzer, collected reviews from Amazon from different categories. And the idea is to train on one and test on the other. And so back then, here's kind of what's the state of the art. And the winner actually was a deep network, stack denoising autoencoder by Joshua Bengio's group. And I will get in a minute into how that works. But one thing is very interesting, although stack denoising autoencoders are way better, they are much slower to train. That was actually trained on GPUs, whereas these were trained on CPUs. So, it's a massive difference. And so the holy grail, of course, go here, right? You basically want to have low error. There's the transfer ratios. How much does your error increase by going to a new domain? But you also don't want to spend all that time training it. All right, so how does a denoising autoencoder work? And denoising autoencoder, basically, essentially what we're doing here, so this approach by Joshua Bengio, is you learn a new representation of your data that's kind of cross-domain, and then you just use a linear classifier. And so here's how you do this. They take a review, they randomly remove words, and now you can see how this relates to data augmentation. Remove words, and then you try to reconstruct, train a neural network to reconstruct the original data point from the corruption. So I remove some words, and then I try to predict which words did I remove. Like, what did this look like before the removal? If you think about this, actually, this is a bag of word vector. It's multiplied by a matrix, then you get your hidden state. Then it's multiplied by the matrix, and you get the original, the reconstruction. This is actually very, very similar to word2vec, like vector embeddings, because if you multiply a bag of word vector by a matrix, you actually get, word embeddings. And essentially, how is word2vec trained is basically you're saying, I take the words around you, I remove a certain word from a sentence, and I try to predict it from its surroundings. That's exactly what this is doing too. So it's no surprise it works so well. The big difference between word2vec was that Joshua's approach was global. So you took the whole document and removed words, versus word2vec just took a sentence and removed a few words. That's the difference. Okay, and so what we looked at this and we thought, well, actually that's a form of data augmentation, right? That's actually, in some sense, you take this marginalized version, you try to reconstruct the original data point. So one thing we could do is we can actually remove the hidden layer and then use our marginalized corruption. So we say we take a corrupted version and we try to reconstruct the original, and we can take the expected loss again and use exactly the trick for marginalized corruption. And so the nice thing is now instead of training a deep neural network that takes a long time, this is a formula, we can just do it in closed form. So here's actually the closed form solution. It's just a few lines of MATLAB or Python. And while a neural network, of course, can be deep, but we can also stack this, right? We can actually just take, we do marginalized corruption. So you basically, you take a vector, you denoise it, and then what you do is you take that denoised version and you denoise that again, and you denoise that again, and you just always apply some nonlinearity in between. So each one of these is just closed form solution, where you essentially just say, okay, I'm taking a vector and I'm learning a mapping that if I corrupt it, how to reconstruct the uncorrupted version. Essentially, what you're doing here, let me just go back just to give you some intuition here. When I'm doing this, I'm saying, here's a corrupted version. I'm learning a mapping that goes from the corrupted version to the non-corrupted version. What am I doing? Essentially, what I'm learning is which words co-occur, right? I'm learning that if you say, battery life, great battery life or amazing, then you also often say great and other words that are positive. So I'm filling in positive words. And that's why it goes from one domain to another, because the domain specific words, I learn which general words kind of co-occur with those. And those make sense in the other context too. If I run this on a data set, what you get is actually, there's that, if you run just one round of denoising, it does fairly well, it's very, very fast. And then you just denoise the denoised version, you keep doing this. That's kind of our equivalent of adding more layers. And, you essentially actually get the same results as a deep network, but two orders of magnitudes faster. I'm running a little bit out of time, so let me just say a few more things. So we of course tried this subsequently to do this without removing the hidden layer, and so the year we did this actually, we told everyone use blank out. That's what we called it. The same year, Jeff Hinton had this different paper on dropout, but basically you're saying you remove hidden nodes in the middle, you remove hidden nodes in a neural network. So you could use the same trick to marginalize our dropout. And that's a paper I had with Yasha Bengio, but it essentially follows up on this. You could also use this for, finding tags for images, the same trick. And other people have actually used this for link corruption. So if you have, today was a lot of talk about graphs. So let's say we have friendship graphs, and then basically what you can do is you can say we corrupt this graph by removing friendship connections, and then you try to reconstruct them. And so essentially what you're doing is you're imputing friendship networks, and so that's helpful in certain biology tasks like protein-protein interaction networks. Okay, good. In summary, this is work that we did a couple of years ago. We called it marginalized corruption. But the idea is basically you do data augmentation, but instead of really doing it, you marginalize it out, right? And you get a new loss function that handles the limit case of what if you do infinite amount of augmentation for every single sample. And the nice thing is it's a very general framework that you can use in many different settings. These are my co-authors at the time, my former students who are now all moved on to various places, and my faculty co-authors. Thank you. Any questions?
Thank you very much, Kilian. It's really interesting to hear these kind of ideas from several years ago, and they're still super relevant and super interesting. So, a question from Juan Cervinho: what is the intuition behind the results for Poisson noise in the CFAR10 case? Why, intuitively, why do you think Poisson is the one that generates the best results?
A very good question, actually. Why is Poisson a very good case noise model here? And that's because we use bag of visual words. So you basically find interest points in an image, saying like how many edges and so on you find. And so Poisson noise just says I'm perturbing that count. So I may just increase, let's say you have certain edges that are very specific to cars, or, certain interest points that are specific to cars. You may see 3 in that image, but you may have also seen 4 if you may have seen the car in a slightly different angle, or maybe 2, and so on. So you vary that a little bit. And so it turns out that that's essentially what the Poisson distribution is doing. The same actually for words. So for words, also Poisson distribution, like bag of words, vectors, and text. Poisson distribution is a nice corruption distribution, because essentially what it's saying is, well, the word amazing appeared 5 times in this text document. If it had appeared 7 times or 4 times, it wouldn't have changed very much, right? It's still the same kind of document. So you can just, don't put too much emphasis on the exact number that you have for each of these counts.
Great, thank you. And I actually also have like a kind of like historical question. So you mentioned that there's this marginalized general framework for marginal likelihood. Is it fair to say that like it kind of, so I'm aware of this work from Chris Bishop from '95, which kind of shows that training with noise is equivalent to Tikhanov regularization. So that's like a very special case of this general framework.
Yeah, but they also did it explicitly. But yeah, I think that's right. So I think that's right. But I believe I can't remember actually in this paper, did they already do the marginalization? I know Olivier in 2001 did it. He actually used the expected value of this. So I don't remember. I know the paper, but I don't remember the exact details what they wrote. But I think you're right. So essentially, they looked at one of the cases where they were the first to show that it's actually helpful, right? Which is amazing.
Yeah, so I don't think I remember the details, but I can check later. Another quick question from Abhinav Agarwala. So can we use a marginalized version of cross entropy and do away with data augmentation as is common for computer vision? Can we, and maybe that's 2 questions actually, because the second one is, can we use multiple corruptions by just adding them in the modified loss?
So, wait, so the first question was, you can use it for neural networks and computer vision?
Yes.
Cross entropy?
Can we use a marginalized version of cross entropy and basically no more need for data augmentation?
Yes, the answer is yes and no. So yes, he can probably do it. Basically just have a different loss function at the very end. And so, I mean, cross entropy is essentially just the log loss, right? So this Jensen inequality in upper bound would work here. It doesn't capture all cases of data augmentation. Like our case only works for if each dimension is corrupted independently, which actually makes sense in the last layer of a neural network, right? Because then, they're somewhat more decorrelated. For images at the beginning, right, of the actual raw input image, pixels are highly correlated, and other augmentation methods seem to make more sense. For example, if you flip the image horizontally, right, you're encoding something that, you as an expert know is true, that, for example, if let's say you have pictures of cars, if you flip a car, it's still a car, right? That's something that's external knowledge that you put in that that you couldn't know otherwise, right? If you were to flip it horizontally, it wouldn't be a car anymore. It would be weird, right? Sorry, vertically. If you were to flip it vertically, it wouldn't work anymore. So you're telling us in our world that you live in, horizontal flipping is okay, vertical flipping is not okay. You can't get around that, but you can probably still improve things if you use it as the loss function at the very end.
And I guess the second question, just very quickly, can we use also multiple corruptions, maybe like a composition?
Oh, yes, absolutely. That's a very, very good point. So in the MCF framework, so of course, in DeepNet, of course, you can just corrupt at the beginning, at the end, or in the middle of the layers, right? But also in the MCF framework, the only assumption is that each dimension is corrupted independently from all the other dimensions. How you corrupt each dimension is totally up to you. So you could use blank out, you can use Poisson, you could even do sometimes blank out, sometimes Poisson, etc. Like that's all, everything is game.
Great. Yeah, thank you very much for those explanations. And then thanks again also for the talk, and we can